Well, hello, and welcome to Lesson 4 in our Math 221 Calculus 1 at SUNY Geneseo. This lesson will take a look at what we mean by the limit of a function, and that's an interesting question to consider because last time we talked in class about what it meant to get sort of close to something and what that meant for some other quantity. Generally speaking, when we take a look at functions, you got some function looks like so. This is some f of x. And you have some point of interest, maybe that's a, and you might be interested for some reason in what is happening to this function close to a. As we get close to a, whatever that means, and we haven't talked about that yet, but we will. Sometimes the functions get a little bit more complicated, not because they turn green, but because, well, they get a little bit more complicated, and we're interested again in what happens as we get close to this particular x value. So what we'll do over our next 4, 5, 6 lessons is take a look at this idea of a limit. The limit, this idea of what is happening to the function as we get arbitrarily close to some number a, arbitrarily close to some number a. You may have covered this idea in a pre-calculus class. If you did, then this will be a lot of review. This is what Strang and Herman put in the middle of their book, and we should take a look at the language. So we're going to let f of x be a function. It's defined at all values in an open interval containing a. Maybe at a, maybe not at a. Doesn't matter if it is or it isn't. We're going to let L be some real number. If all values of the function approach L as x gets close to a, then we say that the limit of f of x as x approaches a is L. The limit of f of x as x approaches a is L. That's the way we say it. The limit of f of x as x approaches a is L. The real main idea here is that f of x gets close to L and stays close to L. And then this is the way we write that because mathematicians like notation that keeps things brief. Limit of f of x as x approaches a is L. You'll find that right in your textbook, and that's an important deal. So you might wonder, well, what does that look like? This is the function sine x over x. Let's imagine for the moment that we want to find the limit of sine x over x as x approaches 0. Here's x equals 0. It looks like the y values are pretty much halfway between this is 0 and that's 2. So we would think that that's 1. We would think that that's 1. We can confirm that. I've set up the table here so that we can ask the machine what the values of that function are at values that are close to 0. So you may think, well, 0.5 is pretty close to 0, and that number is pretty close to 1. And you think, well, maybe 0.5 is not close enough. What about 0.1? Well, that value is definitely really close to 1. Or we could get closer to 0, or we could get closer to 0, or we could get closer to 0, and it appears that the closer the x values get to 0, the closer the y values get to 1. So we might say that the limit, and I'll go back to the other screen for a moment and we'll talk about how to write this. We might say that the limit of sine x over x as x approaches 0 is 1. And that's reasonable because all of the values here get closer and closer to 1 as the x's get closer and closer to 0. So a table can help us confirm. You might also wonder, well, maybe that only happens as we come this way. What if we pick negative values of x? And the answer is, unsurprisingly, pretty much the same thing. We can get arbitrarily close to 0 on the other side, and we'll get really close to 1. This is basically 1 to 12 decimal places. So that's some notation. I will throw in an OYO here. OYO is short for on your own. This is on your own. It's one of those things people used to do in chat rooms back when chat rooms used to be a big thing. You may want to take a table and try to find the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Notice that you're not going to be able to just substitute 9 in for x because I don't even know what that means. So it might do you well to graph that and then to try values of x that are close to 9. Similarly, you might want to take some time and take the limit as x approaches 2 of x squared minus 4 over x minus 2. It might be worth your while to graph this function. It'll have a hole at x equals 2, and then try some values of x that are very close to 2, 1.9, 1.97. We can get ourselves arbitrarily close to 2. Those are things you might want to try before we gather. I would encourage you to do that. We should also, oh, we don't need that at all. That doesn't even need to be there. Let's get rid of that. There, that's no longer there. Sometimes we get limits from tables, and sometimes we get limits from graphs. So this is some graph of some function f of x. It's got a dot down here. It's got an open circle here, and it carries on like so. This is f of x, carries on like so. And we might ask ourselves what the limit of f of x is as x approaches a, where this is a. And, well, it appears that in the neighborhood of a, the y values are getting awfully close to this, whatever it is. This is some number f of a, and it does appear that the limit of f of x as x approaches a is whatever f of a is. We might also ask about the limit as x approaches b. The limit as x approaches b of f of x, the limit of f of x as x approaches b. So, well, what is that? Well, as we get closer and closer to b this way, function values get closer and closer to this number right here. Whatever this number is, we'll call it heart, whatever that is. And as we get closer and closer to b from this side, the y values get closer and closer to heart. And so we would say that the limit of f of x as x approaches b is heart, because no matter how close I want to get to x equals b, the y values are getting very, very close to whatever this number is. Now, some of you are going to say, wait a second, magic pen, that's where the function is at b. And I agree with you that the function value at b is this number down here. It's not heart. But the limit doesn't care what the actual function value is. The limit cares what happens as we get close to that function value. I'll throw in a quick side note here. This will help out people who may have seen this stuff before. When we take a look at that hole in the graph, we sometimes consider x values coming this way and x values coming that way. If we consider them coming this way, then we're talking about the limit of f of x as x approaches b from the left. And that little minus sign, it's a superscripted minus sign. That minus sign means that we're approaching from the negative end of things. That limit happens to be heart. Similarly, when we come at b from the right-hand side, we would say that the limit of f of x as x approaches b from the right, and that's a superscripted plus sign, is heart. And so it is fair to say, and in fact we will say, that the limit of f of x as x approaches a is L if and only if the limit of f of x as x approaches a from the left is L, and the limit of f of x as x approaches a from the right is L. And that sort of makes sense because if we were coming from the left and we were coming from the right, and we weren't getting the same number both ways, we couldn't talk about what's happening at x equals a. We could only talk about what's happening from one side or the other. I want to do one other thing in this screencast. So I figure we've got about 5 minutes left. So you don't need to hit the bathroom just yet. Let's do one other thing. Not that thing. That thing. Let's take a look if we can. I'll get rid of the table. And I'll get rid of this function and replace it instead with this function. This is f of x is the sine of 1 over x. And what I'd like us to do is to consider the limits of this function as x approaches 0. As x gets closer and closer to 0, what is happening to that graph? That's an interesting question. It's really hard to see what's going on here, so what I'll do is I'll give us some context. I'll say let's change the window so it's just -1 to 1. And well, that's not very helpful. That doesn't really tell us anything. So I'll change the window. I'll go from -0.1 to 0.1. Oh, golly. And you're still not seeing what's happening. And maybe I'll change the window. And you're still, it's just weird, isn't it? It's just weird. It looks like the function just keeps bouncing back and forth, harder and harder the closer we get to the y-axis. And you know what? That's exactly what happens. And since that's it, pardon me, that's exactly what happens, what we say is the limit of the sine of 1 over x as x approaches 0 does not exist. Some people abbreviate this DNE. Does not exist. This is what we call an oscillating discontinuity. And we'll talk about continuity in a little bit more depth as we go. Moral of the story here, limits do not always exist. We know that from watching Mean Girls. The limit does not always exist, but certainly in this case, from a mathematically rigorous standpoint, we know that the limit does not always exist. It is also possible for a limit not to exist because the graph does something like this. Let's suppose this is x equals 3. And let's suppose that this dotted line is something you learned about in high school called an asymptote. And if that thing is what we call an asymptote, then we would say that the limit as x approaches 3 from the left of f of x appears to be that this thing goes up, 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 and it never ever stops, and it increases without bound. And when it increases without bound, we call that limit positive infinity. We say that the limit is positive infinity. Similarly, if we want the limit of f of x as x approaches 3 from the right-hand side, as the numbers come at 3 this way, that function goes down, 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 and it decreases without bound. And if it decreases without bound, we say that that limit is negative infinity. And so what you'll find in a way that we can actually talk about, anytime there's a vertical asymptote for a function, one of the limits, either the limit from the left or the limit from the right, or both, is one of the infinities. Maybe the limit from the left is and the limit from the right isn't. Maybe the limit from the right is and the limit from the left isn't. Maybe the limit from the left and the right go to both infinities, one to the one, one to the other. But if one of the limits from one of the sides is one of the infinities, you've got yourself a vertical asymptote. On your own, before we gather, you may want to take some time and take a graph of x squared minus 1 over x minus 2. You may want to put that in your graphing calculator and take a look at values of x close to 2 but on the left-hand side and see if you can identify the limit. If you're looking for practice before you come to class, and you are looking for practice before you come to class, find section 2.2 in the PDF of the Strang Herman textbook and give a shot at 35 and 43 and 46 through 49. They're kind of bang bang, and 77. Those are questions for you to consider as you get ready for class next time. Okay, thanks very much, everybody. We'll see you then.